not working very well. All right, so we were looking at the jump it problem in the last lecture. Now that particular problem has some nice properties that make it relatively easy to solve. So first of all, the rules of the game make it impossible to move to the same square twice. Right, so in jump it, you're always moving to the right. There's no way to move left in that game. Furthermore, because you can only move 1 or 2 squares, it's impossible to move off the board. Right, so there's no, whenever you land on a square, there's no way to, you can always move from that square to make progress to the solution. Now, you can change, or you can modify the way that game works in the following way. So it's a similar board setup as jump it. You start on the left-hand side of the board. You want to go to the right-hand side of the board. The board is made up of a bunch of squares that have a positive integer in them, except for the last one. The last one's always 0. Every other square is a positive number. And now when you move to a square, that's the number in the square tells you how many locations you can move left or right. So now you have a choice of going forwards or backwards, which is different than I'm just okay. Hang on. Teams is really messed up for me today. Sorry about that. So the number in the square tells you how many places you can go left or right. Now you're not allowed to jump off the board. So if you're on the 3, for example, you can't move 3 spaces to the right, to the left, because you'd end up off the board. So if you're on the 3, you'd have to go to the right, to the 5. Here's a one possible solution on this board. You always start at the left-hand side, and of course you can't move to the left from the left if you're in the leftmost square, so you have to go right. So you go to the 4, right? From the 4, I can't move 4 spaces left, so we go 4 spaces to the right, to the 1. And now you have a choice. You can move 1 space to the left or right. And I think in this solution, we're going to go right. So we'll go to the 6. 6, you can't move to the right 6 squares because you'd fall off the board, so you have to go left. That takes you to the 3, and now the 3 takes you to the 5, and then the 5 takes you to the 0. When you get to that 1, there's actually a way to solve the board if you go left instead. So 4, 1, and now we go left instead of going right. And now we go to the left again, back to the 2. Now, when you're on this 2, you don't want to go right back to the 2 that you came from, because you're going to end up in a cycle, right? You'll just keep. You want to avoid revisiting squares that you've been on before. So we go left, and now we're on the 3. So now we know that there's a solution that takes us to the end of the board. So that 2, those 2 2s that are on the board, that's a bit of a problem when we're writing the solution. When we're trying to write a method that solves a board, because we need some way to detect that we're in a cycle, or we need some way to avoid getting into a cycle, right? So you want to avoid going back to a square that you've already visited. If a board has cycles, then it's easy to make a board where there's no solution. So here's a there's a trivial example of a board where it's not possible to get to the end of the board. And on a less trivial example of a board is this one. So no matter what you do on this board, you eventually end up at the 1. And the 1 leads to a cycle. It is possible to create unsolvable boards, right? And you don't even need a cycle for an unsolvable board. It's possible to insert some number where it's possible to land on a square where it's impossible to move left or right because there aren't enough squares on the board. So landing on the 100, I can't go 100 squares right or left. So this one's an unsolvable board. So like jump it, every time you move to a square, there are, well, sort of like jump it. So in jump it, you almost always have, you can always choose between two possible moves. You either move one to the right or you move two to the right, except when you get near the end of the board. In this game, it's a little bit different. So you don't always have a choice of two possible moves because you're not allowed to move off the ends of the board. But if you have a really, really large board and the numbers on the board aren't very large, then we can say that approximately every time you land on a square, there's a choice of two moves. So to solve this problem using brute force, right, and to look at every possible solution, there's roughly 2 to some exponent number of moves that you have to consider. So that makes it difficult, or more challenging anyway, to write an iterative solution for this problem. Right, so it's not clear how you would how you'd solve this problem using a loop or loops or perhaps nested loops. Now, if you want to try solving the problem with recursion, you have to make sure that every time you call the method recursively, the problem that you're trying to solve gets smaller, right? And it's not immediately obvious that this version of the game, the board gets smaller, right? So in jump it, you're continuously moving to the right, which means you can ignore all the squares to the left, right? So in jump it, it's clear that the board gets smaller. In this game, the board does in fact get smaller because you never want to go back to a square that you've been on before. Right, so every time you land on a square and then make another move, the board gets one smaller because you're not going to consider any solutions that take you back to a square that was visited before. Now you need some way to indicate that in the solution. So what we're going to do is we're going to modify the board every time we step on a square. So when we step on a square, we're going to change the value that's on the board. So we're going to set it to some non-valid number. So we'll use the number -1 to indicate that we've landed on the square before. You can't remove the square from the board, right? Because that changes the structure of the board, which doesn't lead you to the correct answer. So you don't want to remove, you have to modify instead. Now, the recursive cases are pretty straightforward because at every step, you're moving either left or right. So the only thing you need to check for when you land on a square is, can you actually move left without falling off the board? Right. If you can move left, then you move left, and then you try to solve the board after moving left. Right. Now, we can use recursion to solve this problem. Right. So move left and then solve the board starting at the new square. Right. Similarly, at every square, you also have the choice of moving to the right. So we check, can you move right without falling off the board? And if so, you move right and then try to solve the board, and then try to see if there's a solution to the board from the new square. Right? And again, we can use recursion to answer that question there. So we're going to write the following method. The method is called isSolvable. It's going to return true if the board is solvable, and it will return false if the board is not solvable. Index is the square that we're currently on. Right? So when we first call the method, we'll pass in 0 for the index, and the board, the board is just a list of integer values. Now the contract for the method says that the method does not modify the board. Right? So whatever we do inside this method, we have to make it appear as though the board was never changed. Right? Now you don't want to change the board because whoever's calling the method, they're giving you a list that defines the board, and they probably are not expecting the method to modify the board, right? Because they might want to use their list for something else, right? Perhaps to draw the board on this perhaps to draw the board in some way. Right, so if you change the board on them and then they draw the board and it looks different than they expect, it complicates their life. Right. Okay, so how does this work? Well, we're going to use recursion, so we need some base cases, but I'm going to do those last instead of doing them now. So let's do the recursive part first. So we want to answer the question, is this board solvable starting from that index? Okay. We need to get the value of the square that we're currently on. Right now we've got a list here that represents the board. So the way you get an element from a list is with the get method. Okay. So we get the value of the list at that index, and that's the number of squares that we can move left or right. We're currently on this square, so we want to modify the board. Now remember I said that the method doesn't modify the board, or it doesn't appear to modify the board. Right. So internally in the method, we can change the board as long as we undo the change before we return back to the caller. Right. So as long as the caller can't tell that we've changed the board, we are allowed to internally change the board in the method. So we'll modify the board, setting that element of the list to -1. Okay. And we're going to, when we do the base cases, we're going to check if we're on a square whose value is -1, right? If we land on a square whose value is -1, we know that we've come back to a square we visited before, so we want to reject that solution. Right, so that'll be one of our base cases. Okay, next, we want to do the recursive call to see if we can solve the board going to the left. So I want to know, can we solve the board by going left? So I've got a little Boolean variable here. We need to check, can we actually go to the left? Right, so now remember, that's the index of the square we're currently on. That's how many squares we're going to move. So if we go left, the index of the square that we land on is just index minus value. That's an index for a Java list, which means it has to be greater than or equal to 0. Okay. So if that is greater than or equal to 0, we can go left. And so all you do is you recursively call the method, right, and move left. So we move to the square at index minus value, right? So we jump to the left, and then we try to solve the board. Right now, when we recursively call the method, the board has been changed, right? We've indicated that the square we're currently on has been visited before. So this version of the recursive method gets a board that's different than the current version of the recursive method. Right? And we store the answer. Right? So remember, this returns a Boolean value. So we want to know, what is that value? Right? So we're going to set when left to whatever the recursive method returns. If this is true, then we know that the board is solved. There's a solution for the board. Right? If it's false, then we continue. Right? And then we say, well, I couldn't solve it going to the left, so can we solve it going to the right from this square? So again, it's the same thing, right? Index plus value, that's the index of the square after moving to the right, that by that amount. Now that's an index for a list, so it has to be less than the size of the board. So if that condition is true, recursively try to solve the board by going to the right. So when right becomes is solvable, index plus value, move to the right with that board. That board, again, we've modified the board to indicate that we've been on the current square. Okay, so this version of is solvable and this version of is solvable does in fact get a smaller version of the, oh wait, there's a typo. I just caught it. That's board. There was a different solution from the original slides. No, that's wrong too. Is that right? This one's probably wrong. Yeah, it's probably wrong too. Sorry. So the original version of these slides had a different solution on them. So the original version of the slides, we made a copy. I made a copy of the board and then passed the copy to the recursive method. But there's no need to make the copy. You can. It's perfectly solvable doing it this way. All right, so we've explored the board. We've explored the board going to the left with this recursive method. Explored the board going to the right with this recursive method. We've got the answer is the board solvable going left. We have the answer is the board solvable going right. The overall answer is simply the OR of those two answers, right? If we can win by going left, or if we can go by win by going right, then the board is solvable. If they're both false, then the board's not solvable. And so that's the return value. You could also return, if win left is true, you can also return here, right? So there's no need to explore going to the right if you can win by going to the left. Now, we changed the board here, so we have to undo the change before we return the value back to the caller, right? So we reset the value of the board at this index to its original value. And that is the recursive part of the is solvable method. Okay, so the base case, to complete the method, we need to define the base cases. Now remember, a base case in a recursive method occurs when you know the answer to the problem that you're trying to solve. So if you land on a square whose value is -1, I know the answer to the problem that I'm trying to solve, right? The board is not solvable because if we move to that square, we end up in a cycle. The other base case is when you actually solve the board. So if you land on the last square, then you know that the answer is true, right? The board's solvable because you made it to the last square. So the base cases are very simple to write. You land on a square whose value is negative, right? We've been on the square before, so you return false. If you land on the last square, right? Now remember, the index of the last element of a list is the size -1. So if we end up on that square, you return true, and that's it. That completes the method. The rest of the method goes here. When you write these recursive methods, it's very tempting to write to change this condition here, right? So you want to test if you can move to the left, right? And then a lot of people who try to write this method will also say, right? So can I move to the left? And is this value, right? Is the value of the list at this index? Is it positive, or yeah, is it positive or 0? Right. So in other words, a lot of people try to merge this condition with the base case. Right. So they try to merge this condition, boom, in here. Right. But you don't have to do that. Right. That just complicates the method. So it complicates the logic here, right? You have to check when you're testing the method. When you go to test this condition, right? You need to test both of those things. You need to you need to test that both of those conditions are true, which complicates your life. Right? It's much simpler just to write the base, just to write a base case that checks if you land on a square that you've been on before. Okay. So that's the complete method for is solvable. All right. Anybody have any questions about that particular method? All right. Look at another problem involving recursion. So in CISC 121, they should have taught you about sorting. You may have seen a method called selection sort. You may not have it. There's lots of different sorting methods, so you can never tell what what students learn or what sorting methods students have been taught. There's a method called selection sort that you probably learned how to implement using loops. I'm going to implement it using recursion just to show you that it can be done. So we're going to start by writing a recursive method that moves the smallest element in a list to the front of the list. Right now, you can easily do this with a loop. Right? You write a loop to find the smallest element, or to find the index of the smallest element. Right? And then you can simply swap the first element with the smallest element. right? So just switch the first element and the smallest element, and that moves the smallest element to the front. So that's relatively straightforward to do with loop. It's less obvious how you do it with recursion. So here's a picture of how you would do it with recursion. Now, when you're writing a recursive method, you have to get into the mindset that you're using recursion to solve a smaller version of the problem. Okay, so that's what you always have to be thinking when you're trying to write a recursive method. So I want to write a method that moves the smallest element in this list to the front. And look at the list and know that I have to move the 0 to the front. And now the problem is, how on earth do you do this using recursion, right? And so the insight that you need is that you want to solve a smaller version of the problem. So what happens if I take the list that doesn't include the first element? What if I move the smallest element in this sublist to the front of the sublist, right? And so does that actually get you closer to the answer? So that's the question you need to ask, right? So if I move the smallest element in the sublist to the front of the sublist, I end up with the following picture. Right? I don't know what the elements, like what order the elements are in the rest of the list. Right? I know that the numbers 1 through 7 have to be here, and 9, but I don't know, or I don't care, how the method has modified these elements. Right? So they could have jumbled up these numbers somehow when it moves the 0 to the front. Right? We don't care. All that you care is that the 0 is here. Right? And now you can realize that, oh, if I can move the 0 here, then all I have to do is compare these two elements. Right? If the 0 is smaller than the 8, I switch the 0 and the 8. Right? If the 0 is not smaller, then that number must be the smallest number in the list already. Right? And so, and that's it. Now you've got your recursive solution. Right? Solve this problem using your method by recursively passing in the sublist, not including the first element. When that recursive method returns, compare the two elements at the front of the list and swap them if you have to. And that's it, right? So that's a very different way of thinking than using iteration. The natural solution to this problem is to say, oh yeah, just find the minimum element in the list. So, right, look at all the elements and say, oh, it's the 0, and then switch the 0 and the 8. Using recursion, it's a completely different way of thinking. So this is the min to front method, right, that moves the minimum element of the list T to the front of the list T. Right? All the other elements in the list should be somewhere in the list T. Right? So in other words, you're not going to remove any elements or change any elements. Right. But otherwise, the smallest element should be at the front of the list. All right. So let's ignore the base case for now. The way the recursive method works is you just move the smallest element in the rest of the list to the front of the sublist. Right. So we use the sublist method here. In the sublist that does not include the first element of the original list. Right. So in other words, we start at index 1 of the list T, right? And we use T.size to indicate that we want all the other elements of the list. Right. And we simply move the smallest element. We rely on the min to front method to move the smallest element in the sublist to the front of the sublist. Now you just compare the first two elements in the original list. So the first element in the list is T get 0. Second element is T get 1. And now you just compare the first and second elements. Right? So if the second element is smaller than the first, set the first element of the list to the second element. Set the second element of the list to the first element, and you're done. That's it. That solves the problem. Now, what's the base case? Right. So remember, the base case occurs when you know the answer to the problem. Right. So when do I know that the smallest element is at the front of a list? Well, if the list has size 1, I know that the smallest element is at the front of the list. Right. What you have to be careful about here is to you also have to realize that someone might call this list with an empty list. Right. in which case you have to decide whether or not that's an error, right? So if it's an error, you have to check here, right? Is the list empty? And if it is, throw an exception, right? You can also decide to say that if the list is empty, then we're going to do nothing, which is what I've chosen to do here, right? So this base case here is if the size of the list is 1 or 2, 0 or 1, right? Then we're going to return do nothing, right? The front, we're going to the list already has the smallest element at the front, or it's empty. Right? So you can that's a suitable base case in this problem. Once you have the min to front method, you can easily implement the selection sort method recursively. Right? So if I call min to front once, that moves the 0 to the front of the list. Oh, where are we looking for the small? Where are we looking for the smallest element? That's the magic of the method. That's why I said it's very different. This is a very different way of thinking than using iteration, right? So the answer is every time you call the recursive method, right? So every step of the recursion, you're looking for the smallest element in the rest of the list. So when I recursively call the method, I'm looking for the smallest element that's in here. Now, when you call the method recursively, the first thing you're going to do is you're going to check for the you're going to look for the smallest element that's here, right? That's going to look for the smallest element that's here. That will look for the smallest element that's here, and then here, and then here, here, and then here. Okay, so eventually you get down to the point where there's a 9 and a 1, right? And then we call the recursive method again, and we get to the 1, right? Now that recursive method returns because we're at a base case. Right? When that method returns, the recursive method that's looking for the smallest element in the 9 and the 1 now compares the 9 and the 1. And it switches these two values. So now you have the 1 here and the 9 here, right? And then that method finishes. So now this recursive method, right, continues to run. So you have a 2 here and you have a 1 here. So now these two switch and the 1 is here. Right? And then that recursive method finishes. This version of the recursive method now continues to run. It's got a 0 here and a 1 here. So no switch happens. So the 0 is here. Right? Now this version of the recursive method continues to run. You've got a 5 and a 0, so these switch. Right? So that's what's happening. It's like I said, it's a very different way of thinking than using iteration. You have to get used to doing this though, because well, at least for those of you who are going to take CISC 235, the data structures course, because in CISC 235 you're going to be working with trees and other linked structures, and on those types of data structures, it's often much easier to write a recursive version of a method than it is to write an iterative version of the method. So it's a useful exercise to practice recursion now rather than trying to deal with it when you hit 235. Okay. So suppose I've called min to front once already. Does the code automatically return to there? Yes, that's the other thing you have to remember about recursion. It's not on these slides. I should have included it. Every time you run a method, it's not the same method that runs every time. Right? So if I call min to front, right, then there's a little chunk. Oops, sorry. When I call min to front, a little chunk of memory gets carved out for min to front to run in. Right. Now, if min to front is recursive, it calls itself. Right. So when it calls itself, there's a new chunk of memory that gets carved out for the recursive version of the method to run in. Right? If that method calls itself, then another chunk of memory gets carved out for the recursive method to run in. Right? If this version of the method reaches a base case, right, then it returns back to the one method that called it. Right? So now you're back in the second recursive method. This one runs until completion, and then it returns back to the recursive method that called it. So that's what you have to, that's one of the steps that they often don't teach you when you first see recursion. Right. I probably should, if I remember to do it, I'll put some slides in that show you exactly what happens when you call a method. And hopefully that clears things up. A lot of students think that when you call a method, right, so when I call them in the front, it's running here. And if I call it again, it's still running here. That's not what happens. Every time you call a method, you get a new version of the method. Okay, so I've called min to front once. Once you see that actually, I'll do that next lecture. So I'll explain exactly what happens during recursion. Okay, if I called min to front once on this list, I end up with the 0 at the front, right? And now you can say, well, what if I call min to front on the sublist? Right? So what if I call it again? Well, that moves the 1 to the front of the sublist. Right? Now I've got the 0 and the 1 in the front. And what happens if I call min to front again, this time with the rest of the list, right? So the sublist not including the first 2 elements. Well, that moves the 2 to the front, right? So now I've got the 0 and the 1 and the 2 at the front. So what if I recursively call min to front again, this time ignoring the first 3 elements? Okay, well, now the 3's there. And if you keep on going, right, end up with a sorted list. Right? That's selection sort done recursively. Right? So all you do is you just keep on calling min to front, right? And you shorten the list by 1 every time. Right? So move the smallest element to the front, I get the 0. Now move the smallest element in the rest of the list to the front of the rest of the list. Right? And you just keep on repeating, and that gives you a sorted list. Right? So that's selection sort implemented recursively. And the recursive implementation is 3 lines long. Right? Assuming you have min to front already. Right? So if you have min to front, then selection sort simply calls itself, right? Passing in the rest of the list every time, right? The rest of the list not including the first element. Right? How long do you run this for? Well, as long as the list is bigger than 1. So in other words, as long as there's still something left to sort, you just recursively call the method. Right? You don't have to, when the list is size 1, it's already sorted. So you don't have to do any more work. Right? If the list has size 0, it's already sorted. So you don't have to do any work. Right? If the list is bigger than 1, well, just move the smallest element to the front of the list and then sort the rest of the list. So if you learned selection sort, and I'm not sure that you did, you almost certainly would have used a loop, right? If you implement it using a loop, there's some bookkeeping that you have to do, right? So it's a little bit tricky to do the bookkeeping. The alternative way to implement it is using recursion, right? But to implement it using recursion, you have to figure out how to do min to front, which isn't exactly obvious. In practice, you would not use recursion to implement selection sort, right? You would use iteration. And I guess in the next lecture, you'll see why you would not normally use recursion, right? People will say, well, you don't use recursion. So when we first teach you recursion, you'll often be told, look, you would never do this using recursion because of reasons, right? So in the next lecture, I'll show you the actual reason. Don't worry about this. This is just doing the computational complexity of selection sort. So just ignore this slide. Well, read it if you want to, but I'm not going to ask you about this. Oh, okay. So that takes care of the list lecture. I guess before I move on, I want to talk about sets next. Anybody have any questions about lists? All right. Not seeing any right now. So the next assignment, which will appear today or tomorrow, you'll have to work with some lists to do some hopefully interesting operations. All right, now what about sets? Okay, so a set is a collection of unique elements. So that's the Java definition of a set. It's also the mathematical definition of a set, right? So the set of integers is the it's the set of all unique integer values. So in a set, no two elements are equal to one another. Right now, you might ask yourself, why would you want to do this in a programming context, right? And it turns out there's lots of reasons why you want to do this. Reason number one is so sets are much faster at determining whether or not an element is in the set than a list or an array. Right? If you have an unsorted list or an array and you want to know does the list or array contain a particular element, you potentially have to look at every element in the list or array. So it's big O of n for contains. In a set, sets can do it much faster. One type of set can do it in constant time, so big O1. Another commonly used type of set can do it in O log n time, both of which are much faster than ON. So if you need to determine whether or not something is in a collection, sets are usually faster, or well, they're almost always faster than using a list. Sometimes you've got a list or an array. It has a bunch of elements in it, and one or more of the elements are duplicated, right? So there's more than one value that's equal. There's one or more values that are equal to each other in the list, and you want to remove those duplicates, right? Then the easy way to do it is to just take the list and dump it into a set, and the set will remove all the duplicates for you. Similarly, if you want to find the duplicated elements, then there's a way to do that using sets as well. If you want, sets are, they model the mathematical the definition of a set. So you can do set intersection, set union, and set difference as well. Right. So any application where you have to take an intersection or union, sets can do those. They have methods that can do those for you. Right. You don't have to compute. You don't have to compute the intersection or union yourself. Now, the other big reason you need to know about sets in Java is because Java maps, they use sets. So in order to use a map, you need to know how to use a Java set. One of the confusing things about sets when you first start using them is that there's no indexing, right? So with a list, you're used to, it's one of the common things that you do with a list is you ask for the ith element of a list, right? I want the fifth element of a list, right? You can't do that with a set. So sets have no notion of not all sets. So sets have no notion of indexing, right? So I can't randomly pull out an element from a set. So that's a bit weird when you use sets for the first time. So sets in Java are similar to Python sets if you used a Python set. I don't know if you did. It doesn't matter if you did or you didn't. It turns out sets, you can use them in a way that's similar to using lists as long as you don't use indexing. Right? So when I show you some of the set methods, they're going to look exactly like the list methods. Java gives you many different types of sets to use. Normally, you pick between 2 or 3. So there's 2 main kinds plus a third that's occasionally useful. So there's something called a hash set. All the sets are in Java. All the sets that we use are in Java util. So they're in the package java.util. If you used a set in Python, then the set you use looks like a Java hash set. There's also a tree set, which is commonly used. So a tree set is a set that sorts its elements, which is occasionally useful. Oh, I don't have the third type here. Okay, there's a third type here called a linked hash set, but I guess we're not going to look at that today. I thought this lecture. Hang on just a second. I just want to quickly jump through. Oh, there it is. Okay, so it is here later. It'll show up later. These are the 2 main kinds. The linked hash set I'll explain in a few slides. It's occasionally useful. Like lists, Java sets are generic, right? So they hold elements of one type. Just like using the lists, you have to specify the type inside this less than and greater than, this diamond operator. Make a hash set, for example, of string. You would write hash set less than string greater than. Okay, so that's a hash set whose elements are strings. You call a constructor to create the object. Right? When you call the constructor, as long as there's a type declaration on this side, you can. That's not true. The type declaration on the left-hand side, you don't need it here. Right? So you can just use the empty diamond. I'm going to write this here. Right? If you have an existing, so do something with t. Now, if you have an existing variable that already refers to a hash set, right, then you can also write this, and then make a new set. Right. So if you have an existing variable t that's already that's already a hash set of string, then when you make when you call the constructor, you can still leave the type out, right? Because the compiler can determine that the type that here it has to match whatever type t was declared with, right? So t was originally declared as a hash set of string, so the compiler can figure out that you mean hash set string here. Just like lists, you can't make a hash set of int. Right? You have to make a hash set of integer instead. It's a generic type. You can't use a primitive type for the generic type. Okay, here are the common set operations. So notice that this list is much shorter than for lists, right? So these are all they actually all look the same as the list operations. But get and set are missing from sets. Right. So to make an empty set, you just call the no argument constructor. Want to check is and set empty? There's an is empty method. Want to know how many elements are in a set? That's the size of the set. Want to add an element to the set? It's the add method. Right? Now, add for sets, you don't know where the element's going to go when you put it into the set. Right? Well, unless it's a sorted set, and then you know that it's going to go into the set so that the set's still sorted. If you're using a hash set, you have no idea where that element's going to go inside the set. You want to check if a set contains an element, right? That's the contains method. Does the set T have an element that's equal to val? Is what contains. Contains for sets is much faster than contains for lists. If you want to remove an element, there's only one version of remove, right? So in lists, you can remove by index. For sets, you have to remove by an element. Right? So remove elem will remove the element that's equal to elem if such an element is in the set. Right? If it's not in the set, then remove returns false and does not change the set. To copy a set, just use the copy constructor. And those are the common methods for sets. So you can't actually do much with a set. Basically, you can put things into it. You can ask, does the set contain a value? Right? And then you can do intersection, union, and difference. Okay, so hash set is extremely fast. So you can add, remove, or ask the hash set if it contains an element in 01 expected time. Right? It's possible. It is possible to make the hash set have worse than 01 time, but that would be unusual, right? So the element types that you're putting into the set, or the elements that you're putting into the set, would have to be a little unusual for that to happen. Right, so this is 01 expected complexity. Worst case, it's not 01, right? But for most use cases, hash set's very fast. The problem with hash set is you don't know what order the elements are in the set. And you can iterate over a set. I'll show you how to do that in just a minute. The problem with hash set is you can put stuff into the set and then the order of the elements change. So you can't rely on, if you then iterate over the elements of the set, it might be different. The order might be different than when you iterated over the elements of the set previously. Your other choice is tree set, right? So tree set keeps things in sorted order, but because it keeps things in sorted order, it's a little bit slower than hash set, right? So add, remove, and contains are fast, so generally faster than a list, but it's slower than hash set. So for a tree set, you have O log n guaranteed complexity, guaranteed worst case complexity. And the elements are ordered by their natural ordering, which means they're sorted. Now, in order for the tree set to sort its elements, the element type has to be sortable. Right? So whatever the element type that you put into the set, it needs to have a compare to method. Okay? So remember, string has a compare to method that lets you compare strings by their dictionary order. So you can put strings into a tree set without any issues. If you have an element type that does not have a compare to method, then you have to do something else instead. You can still put them into the tree set, but then you have to supply some extra information. So we'll look at that a little bit later on when we look at compare to. There is a third kind of set that is occasionally useful. So there's something called a linked hash set. And so it sort of gives you the benefits of a hash set and a list. Sort of, not exactly, but sort of. So it's very fast add, remove, contains. Right, so again, it's O1, expected complexity. It's slightly slower than a regular hash set. So when you put things into a linked hash set, the set remembers what order you put things in. Right, so if you put in the elements X, then Y, then Z, then the set remembers that you put in X first, then Y first, then Z. Y, X, then Y, then Z. Right, so it remembers the order. And that means when you loop over the elements of the set, it's always the same. Right? You get back the elements in the order in which they were inserted. Right, now, the way this works is that internally, the linked hash set essentially has a list in it. So it has a list that also stores references to the elements. Right, so it's a list and a set at the same time, essentially. And that means your linked hash set has to use extra memory, right? It needs the additional memory so that it can store the order of the elements that you put them in. So it ends up using a lot more memory than a regular hash set. Okay, now you can't index into a, oh wait, I have to stop, it's 20 after the hour, sorry. So I was just about to answer the how do you iterate over a set? Well, here's the answer. You use a for each loop or an iterator. Okay, so I have to stop there because it's 20 after the hour. I have time for questions if anybody wants to ask them. I'll take assignment questions too if you have those as well. First assignment, when, if at all, are we supposed to? Oh, you don't call degree yourself. So we're gonna, when we go to look at your code, we're going to test the degree method ourselves. So we'll call degree from a separate class and see if it's implemented correctly. But you don't have to use it yourself. You can test it yourself, of course, right? So you can write your own code to see if it's working the way you think it is, but you don't have to call it yourself in the main method. Any other questions? Do we need to put our name or student? No, when you submit it on OnQ, we know who it is, right? OnQ tells us who submitted the file. I'm confused on what to do. I don't understand the instructions. Sure, I can explain those to you now if you want. Oh, wrong button. Okay, let me pull up some slides that have a picture of the of a grid. Where did I put that? Assignments. Okay. Oh, wait, that's not right. Sorry. Somewhere I have the picture of the grid. Is it here? Oh, here they are. Good. Okay. All right. So the degree method. So I need so I can just use an empty grid. Let me just quickly duplicate the slide and delete the 4. So the numbers in the grid don't matter for the degree method. Okay. So the degree of a cell is the number of cells that are connected to it. Right now, for our purposes, we're using what's called 4 connectivity. Right. So the degree of that cell there, right, is 4. Right. So it has right. It has 4 cells connected to it. Right. So the degree method looks like text. So the degree method looks like public static int degree index 2, right, and then a 2-dimensional array of cells like that, right? So there's your degree method. Okay, so if that index I, so if that's the index 1, so 0, 1, so row 1, which is the row with index 1, and the column with index 0, 1, 2, right? Then this method should return 4. No, you don't have to declare that it conforms to Queen's standard of academic integrity. That's generally, we just assume I assume that that's the case, right? You don't need a declaration or anything like that. On this assignment, there's no way for me to check anyway, because everybody's code should be identical, right? Because I asked you to translate a program. So everybody should give me back the same translation. Really? Fascinating. No, I only ask you that on a midterm or an exam, but I never asked that for you on an assignment. Okay, so, right, so if you look at the index, right, all you have to do is look at the index, right? So if the index here, because it's row 1 in column 2, you can conclude that it must have a degree of 4, right? Where is, right, so if you're here though, right, so if your cell is here, that's got an index of 2, right? There's only this cell and this cell connected to it. What happened? There's only that cell and that cell connected to it, right? And if the cell is here, then that index is the degree is 3, right? So all you have to do in this method is check, right? If you're on the edge of the cells, then the degree must be 2 or 3, right? So you know that for sure. Someone delete a comment. I just saw. Right. So are we making conditions for I? Yeah, essentially your method is going to look at the row and column that's stored in I, right? And then come up with the answer from there. Right. You also need to know how many rows and columns are in the array though, right? So you have to do 2 things. So first you need to get the number of rows and columns in the array. And then you want to look at the index in the indexes in I. All right, does that answer your question? Any other assignment questions? Is there a reason my program is only running when I run the main method and not the file in my terminal? I don't understand that question. Is there a reason my program is only running when I? So in Java, a program only runs if it has a main method. That's how Java works. So if your class does not have a main method, you can't run it. So if it does have a main method, then when you run the program, it's the main method that starts. So I'm not exactly sure what you're asking. Can I return multiple degree values in one if statement? As long as it's an if, else, if, yes. There's no way to write if and then inside the body of that one if to return more than one value, I don't think. There would have to be another if statement inside the if to do that. But you can use but yes, if, else if, each of the else if parts can return a different value. For sure. There are no stupid questions, Christian. This may be a slight variance. Oh yeah, of course, slight variance is definitely okay. For sure. Yeah, I mean, if you pick different variable names or if you do things in a slightly different order, that's fine. That's not a problem. Right. Assignment 1's here so that you get used to transitioning from, for you guys, from Python into Java. Right. That's the purpose of the assignment. Any other questions? Yep, no problem. You're welcome, everybody. All right, I'm going to leave the. Oh wait, did I stop recording already? Okay, so I'm going to stop the recording.